Okay, welcome to note set number 7, and this is based upon section 2.1 of the textbook. So you'll want to go to the textbook and read this section, either before the video or after, or both, because really the textbook will provide some in-depth discussion of some finer points that perhaps won't come across in the video. All right, so what we're going to do here is continue to explore the solution to AX equal to B. So that's, we're looking at a vector view of this, continuing our understanding of how this works, not just striving for getting an answer. And so this progression here shows how we can go from a set of linear equations, which if we're working on an engineering problem, that's probably where things will start. We'll have that set of linear equations. So if you're talking about circuits, you've written a set of KVL and or KCL equations, loop equations, mesh equations, things like that, node equations. And then from that you can write out the explicit matrix form, but ultimately we can end up thinking about that as just an abstract AX equal to B, regardless of the number of elements that we have, the number of equations and unknowns that we have. Notice that the number of equations that we have is equal to the number of unknowns that we have, and that's why we end up with a square matrix. So that's kind of key. Later we'll talk about what happens if we end up with a different number of equations than unknowns, and those scenarios will be even more interesting and will require even more knowledge of this linear combination view. So in the last set of notes, we had this nice little diagram here that showed when we have a square matrix and we have the equation AX is equal to B, the key dividing decision is, are the columns of A independent, in which case my matrix is non-singular, or are the columns of A dependent, in which case the matrix is called singular. When they are independent and the matrix is non-singular, we can invert A, and then we can apply that inverse matrix directly to B, any B. And for each B, there's one and only one solution. However, for the singular case, there is no inverse, and whether we have a solution or not will depend on whether B is in the plane, or, well, not in the plane, or in the plane. Defined by the columns of A. And if it's not in the plane, there is no solution. And if it's in the plane, there are, for each B, there are infinitely many solutions. So, in some sense, it's this, where'd my pointer go? There we go. Sorry, I had to make a line to see where it was. In most applications, this is where we want to be. If we're trying to solve for the voltages in a circuit, we want there to be a solution, so that would not be good. And we would like there to be only one set of viable voltages. We would not like our circuit to be such that the voltages could be any of these infinitely many solutions. That would not be viable. So when we come to this solution from a physical point of view, if we've done things right, if we've set things up right, we should end up with a system of equations that have independent columns and has just one solution. But in some applications it's not obvious how to ensure that, and so this viewpoint actually provides tremendous insight when we're designing our system. Maybe we're designing a system that's going to take a bunch of measurements. So B are the actual values that we're measuring, and we're trying to figure out what is X. So B might be some like measurements taking, let's put it in a medical imaging viewpoint. So B might be the measurements taken by the MRI system. So MRI is a medical imaging technology. MRI stands for magnetic resonance imaging. So we measure the B that was observed, that results from observing some unknown X through some matrix A. The matrix A ends up depending on our choice of where we put the sensors, the MRI sensors in the machine. And so obviously we would like to set this up so that we end up having one solution. The X that we solve for is the actual image put into some sort of vector form. So this viewpoint is extremely useful in not just solving circuits, but lots of electrical and computer engineering problems. And so what we want to do in this set of notes is convince you that this linear combination view is really the way to go, and that looking at it from the point of view of the individual equations, while sometimes that view has its advantages, in general is actually the more confusing or more challenging point of view. So let's take a look at this. So here's the equation view. So what it'll be clear what we mean by that as we go through this. So if we're talking about a 2D scenario, what we were showing on the previous slide was a 3D scenario where we have three equations, three unknowns. So if we have two equations and two unknowns, so our unknowns can be thought of as being a point in a two-dimensional space. So each equation will define a line. So we would have like we might have like 2x1 plus 3x2 is equal to 5. Yes, 5. So the equation for a line we're used to is y equals mx plus b. It should be an x, mx plus b. But we can solve this, say, for x1. So isolate x1 on one side, swing all the other things over onto the other side, divide by the 2, and we'll get it in this form of y is equal to mx plus b. So in our x1, x2 axes, that top equation just defines a line. And so here's an example. Well, instead of using x1 and x2, here the textbook diagram uses x and y. So you can literally think of y is equal to mx plus b. So here's one equation, and that defines this line, and here's another equation that defines this line, and we say that there's a solution to these simultaneous equations when they intersect. So every point on this line solves this equation. Every point on this line solves this equation. And the only point that solves them both is where they intersect. So that's the solution. In 3 dimensions, we'll have like x, y, z, or as I would write it, x1, x2, and x3. And if you've studied analytic geometry as part of your calculus studies, you've learned the equation for a plane. And it's not surprising that it's going to be just 3 terms that look like this. So you'll have a constant x plus, or a constant times x plus a constant times y plus a constant times z is equal to some constant. So well, let me back up. So in 3D, it's going to define a plane, and the solution will be the one point where all three of those planes intersect. And then we can generalize this in n dimensions. We went from a line to a plane, and then the mathematicians stopped giving unique names to those, and they just say hyperplane. So in general, actually a hyperplane can represent a regular plane, can represent a line. So a hyperplane is just the idea of a plane in a higher dimension. So you can see that a plane is a two-dimensional surface, and so we're looking at a two-dimensional surface in a three-dimensional space. A line is a one-dimensional, quote-unquote, surface, and we're looking at that in a two-dimensional space. So in n-dimensional spaces, each equation would define an n-1 dimensional hyperplane. And where these n hyperplanes intersect, if they intersect at a single point, that's the solution. So next we want to point out that this equation view is really a row view from our matrix point of view. So we start off with and we'll illustrate this in two dimensions. We start off with two equations and two unknowns. We write it in our matrix form. We at least give a nod to the idea that we're viewing this as one of many possible matrix times vector equals vector settings. And so let's look at this, how we connect the equations to the rows of the matrix and the vector B. So we know that to do this multiplication, we would take this and fold it over here, so the x multiplies there and the y multiplies there. So the row gives the coefficients that are in front of the equation, and the second row gives us the 3 and the 2 that are there for that. So let me clear some of this stuff off. And so this is an inner product view of our matrix times vector. We're doing an inner product of the xy vector with each of the rows of the matrix. So that inner product view that we talked about, one of the 4 ways of visualizing matrix times vector, gets us back to this equation viewpoint. And then once we have the equations, we have a bunch of hyperplanes illustrated here with just lines in two-dimensional space. But in general, we would have a bunch of hyperplanes that would all intersect at one solution, one point, and that would be the solution. Now, our linear combination view that we've been looking at is a column view. So if we go from here to here, which we just did, then we can think about going back to this view where the x is multiplying the stuff on this, that column. Let me clear this ink off here. And so our graphical view of this is here's our B vector, which is 111. So that's this point here, and there's the vector that goes from the origin to that point. And our columns are 1, 3, so there it is. Notice how I've got everything color-coded here. And our second column is -2, 2, coded blue, so that's there. And the solution to this is to find the multipliers for each of these, such that the multiplier times each column, and then you add the columns together. So x times 1, 3. So in this case, x would be equal to 3. So we would take 3 times column 1, takes us out to 3, 9, takes us out to this point. And then 1, so y would be 1. 1 times -2 takes us out to this point. And if we add those together, it's like taking this out to this position and adding it together, and we get B. And so that's the solution. 3, 1 tells us that 3 times column 1 plus 1 times column 2 results in the given B. So here's the two views. We've got on the left side our column view, and on the right side our row view. Now I know that you're saying, wow, this row view over here looks pretty easy to interpret. I just draw the two lines that the equations define, and I look to see where they intersect, and that's my solution. And I know that you're looking over here at the column view and saying, how on earth am I supposed to figure out that I multiply that by 3 to get it up to there, and that I don't have to multiply this by anything but 1, and that miraculously they will add together to give that. So in this setting, the row view looks easier, and it is, I'll admit that. And it's actually easier to visualize in this setting, to just simply answer the question of what is the solution. It's easier. But which one will give more insight in the long run? I claim that the column view will give us the insight as to how this all works, and when things will work, when they won't work, and why they're not working, much better than the row view would ever be able to. So even though in the 2D case, the row view seems to be the best, as we go to higher dimensions, that's not true, as we'll see in just a minute. But even more important, the row view is very limited as to what it will tell us about how all this machinery works in general. And it's the column view that really has the powerful insight to how all of this works, and will allow you to apply that insight to designing things like communication systems, control systems, sensor systems, medical imaging systems, all sorts of things, networking systems, all sorts of things that electrical and computer engineers are doing day to day. The row view just does not provide the insight necessary to innovate. The column view is really the driving force in how do we figure out how to do things. And it's that deep insight that allows us to innovate and develop new ideas or understand how to solve a particularly difficult problem. And so this is a big idea in general. So often the easiest way to visualize a problem is not necessarily the most powerful way. So if you're just looking for the easy way to look at a problem, you may be missing out on some very powerful ways of reformulating that problem into something that will give you that aha moment. So if you're trying to formulate some problem and figure out how to deal with it, always ask yourself, is there some other way that I can think about this? And maybe initially it looks harder, but if you dig a little bit deeper, you'll realize, wow, that's exactly what I needed. All right, so let's look further at this column view versus row view for 3 dimensions and see if I can get you to believe me that the column view is the better view overall. So here's 3 equations with 3 unknowns. So we're looking for a solution in 3 dimensions. Can you imagine what the row picture looks like? So now we're talking about 3 dimensions. In 2 dimensions, each of the equations defined a line. If you go back to your analytic geometry, each one of these equations here is going to define a plane in 3-dimensional space. Can you imagine what the column picture looks like? The column picture would be looking at each stack of coefficients as a vector and visualizing where those vectors point to in relation to where this vector points. That's the column view. So I don't know about you, but I can already start to visualize where those 4 vectors lie in a 3-dimensional space, but I can't just look at those equations and visualize what the planes that they describe are going to look like. So already it seems like as soon as we go to 3D, we can start to picture things much better in the column view. So, as we already said, the row picture is going to show 3 planes, and hopefully, if there is a solution, there will be one single point where all 3 of the planes intersect. And the column picture is just going to show 3 columns, 1, 2, 6, 2, 5, negative 3, and 3, 2, 1, that with the appropriate weightings will add to give 6, 4, 2. So, well, let's do this problem with the 3D row view. So we're going to look at planes and how they intersect. So can we visualize the plane that equation describes? Well, if you go back to analytic geometry, or there's some stronger tools available when you study Calc 3 describing planes. But yeah, I'm not able to visualize that. It's much more difficult. So basically it's all the points that satisfy that equation. So let's just try to get a handle on it. If I put in 6, 0, 0, that's certainly going to solve that, right? I'll have 6 plus 0 plus 0 is equal to 6. If I put in 0, 3, 0, I'll have 0 plus 6 plus 0 is equal to 6. And likewise, if I put in 0, 0, 2, that will also solve that. Now, just as two points define a line in 2 dimensions, 3 points in 3 dimensions will define a plane. And so those 3 points will define the plane. So if I plotted those 3 points and then could somehow draw the plane that all 3 of those are on, that's the plane described by this equation. So that's one way to nail it down. Another way, nice computer tool, if you go to this website, Wolfram Alpha, gives you a lot of different mathematical tools. I don't know if you're familiar with those, but I would encourage you to go there and play around with it. It's pretty straightforward to use. There's a lot of examples and so forth. So if you're a little web savvy, you can usually work your way through that. But if you just go there and in the entry window, just type in the equation for this plane, x plus 2y plus 3z equals 6, and then just hit enter, it will actually plot something that looks like this. It'll give you a bunch of other things too, but it'll give you this plot, and so there is the plane corresponding to that. Okay, great. So now we know what that top equation defines. At least we have a picture of it. What about the bottom one now, or the second one of our 3 equations? What's that going to look like? Well, unless the planes are parallel, these 2 planes will intersect, and where 2 planes intersect, we get a line. And so this is the book's rendering of those 2 planes. So it's a little hard to see, but we've got this edge that describes one plane, and then we've got another plane that's going along the black thing in the back, and it really should kind of poke out over here as well, but they don't really show it. But basically you got 2 planes and they intersect at a line, and they're showing the line here, so the line is at least fairly easy to draw. It goes through this point, but the solution of these 2 is every point on the line. So if we have 2 equations and 3 unknowns, we have infinitely many solutions to that problem, as long as the 2 planes intersect. Now, if you try to use Wolfram Alpha, you go and you put these 2 equations in separated by a semicolon. They'll give you an equation that defines this line L, but sadly they don't give you a plot. Okay, now we've got the top 2 equations nailed down. We know what the line where they intersect looks like. And now we add our third equation to that. And so this will be yet a third plane. And so now really, since we know that these top two define a line, we just really need to look to see where, if at all, does that line intersect with this plane. And so there's our view from the previous side, just doing those two equations to find that line. And then here's that line again, so line L. And then here is the plane that is described by this third equation. And so that goes through the line. The line intersects that plane at the point 0, 0, 2. So this set of equations actually has a single point where all three planes intersect, and that is the solution of this set of three equations and three unknowns. Now, that was not very easy. I don't know about you, but I cannot look at those equations and visualize their planes, their individual planes, let alone, easily anyway, let alone take the top two equations and figure out what line I get by intersecting those two, and then figuring out where that line intersects the third plane. So yeah, it's the most obvious viewpoint, and it seemed simple in the 2D case, but now even in just 3D, we're starting to really struggle with this viewpoint. Now, let's try to visualize these 3D, these three 3D equations. So every time we add an additional equation, it reduces the dimension of our solution by 1, right? So we start with one equation, and we've got a plane. Then we had two equations, and we had a line. So a plane has 2 dimensions, a line has 1 dimension. We add one more equation, and we went to a point that has 0 dimensions. So to just think about how these 3D equations could interact, the planes that they give rise to, here's all the different ways that this could play out. So in that upper left corner, we see 3 planes that are parallel with each other. So there's no place that they intersect. So since they don't intersect anywhere, there is no solution for that. Bottom left-hand corner, we've got 2 parallel planes. Those are the ones that are oriented vertically. So they will never intersect. And then the third plane cuts through them. So again, there's no solution. There are, all of these points, and remember, these continue on. We're just showing slices of these planes. All of those points on that line will solve 2 of the equations, but not the third, and vice versa. All the points on this line as it continues will solve 2 equations, but not the third. So that's another possibility. If we look at the next one here, we've got still no solution. So now there are no pairs that are parallel. So there are intersections, but there's no one point where they all intersect. So we could have something that looks like that. And then up here, we have a scenario where the planes all intersect at one line. So all the points on this line here, and remember, it extends on forever. All of those points, any one of those points solves the equations. So there are infinitely many solutions. So we can see that, yeah, this does give us some insight. And we're not saying that we should totally throw this viewpoint away. We're just saying it's not necessarily the most powerful method, and that by going to the column view, we'll end up with much better ways of mathematically visualizing how this all works. And then we've got one solution. Now, you can see that in this diagram that the planes are kind of perpendicular to each other. Doesn't have to be the case to get one solution. but they do all have to all intersect at one point. So our solution would be this point right here. That's the one solution. So now let's think about this same system using the column view. And remember, let's back up. Remember what our solution was. Our solution was 0, 0, 2. And I'll give an admission at the beginning. This problem was set up to make the column view look really easy. So not all problems will look easy in the column view. Remember when we did the 2D case, it wasn't obvious that we had to stretch column 1 by 3 and leave column 2 alone and add them together. And it's not always obvious, but the math works out so much nicer in the column view, and it provides so much more insight. So here's our 3 equations re-envisioned in the linear combination view. So we've got our first column here with x times that. We've got our second column with y times that. Our third column with z times that. And they all, that linear combination is supposed to add up to 6, 4, 2. So the goal is to find the x, y, and z values that will make that happen. So we need to figure out what to multiply each of those column vectors by to produce the b vector 6, 4, 2. So let's visualize that. So plot the 3 vectors in the column picture and figure out what we need to do. So there's the 3 vectors. And luckily, I mean, immediately we can see just from those that there will be a solution, right? And that's so easy to see. But again, if you go to higher dimensions, you're not going to be able to easily see this. But fortunately, we have simple ways to check this. But still, in 3 dimensions, very easy to check and see, oh, yes, all 3 of those vectors do not lie in a single plane. Therefore, there will be one and only one solution to this problem. So that's nice. And so we need to combine these through, multiplying by a scalar. Yeah, so I mean, really, this should say scalar multiplication. I'll see if I can remember to fix that. So scalar multiplication and then vector addition so that we can build 6, 4, 2. So, well, seeing 6, 4, 2 on this diagram is a little hard because our axes don't really go far enough to see that. So we have to make the picture a little bit bigger, at least along this axis, which is the one that the 6 will be along. And so there we plot the column, or I'm sorry, the b vector, and you can just kind of make out the arrowhead for the gold 3, 2, 1 vector, and we immediately see that, wow, the b vector is pointing perfectly along the direction of 3, 2, 1. So really we don't even need the other 2 to build this given b. All we got to do is stretch out 3, 2, 1 far enough to make it be 6, 4, 2. And it turns out that just doubling that, multiplying 3 by 2 gives 6, 2 by 2 gives 4, 1 by 2 gives 2. And so that is our solution for this. And in this example, the column form is very easy to see. And as I admitted earlier, this problem was kind of set up to make this form very, very easy to see. But again, the point of this is not that it makes it easier to see it in an actual picture, but it provides tools that are stronger. And those tools are things that we'll be developing as we go through this course. And those tools will be way better and way stronger than anything that could come from going through the row view of this. So going back to see what we looked at, we saw that looking at how all these different planes are oriented and actually intersect with each other, I mean, we can visualize the generic setups that lead to these different types of intersections. But you'd be hard-pressed to say, well, I need to pick my A this way so that my planes will all intersect the way I want them to intersect, and then be able to solve for some given vector B. So what is our equivalent column view of all this? Well, we've got three vectors. So this isn't for that specific example. This is kind of looking at more generic like this. All we really need to do is look at the vectors and assess, are they dependent or not? So if they're dependent, and I'm trying to show that all three columns here are vectors that lie in this 1-2 plane. So if we think of the 1-2 plane as the floor, all three of these red vectors are lying on the floor, and axis 3 is maybe some pole that goes from the floor up and down, and so all in the left hand side, all three of the red vectors are lying on the floor. So I've got three planes, or three vectors that lie in a two-dimensional plane. Therefore, they must be dependent. And so if my B doesn't lie in that 1-2 axis plane, no solution. If the B lies in that plane, infinite solutions. So neither of those are usually very good outcomes for an engineering problem. On the other hand, over here, we've got this vector and this vector lying in the 1-2 plane, just like we had before. But now the third vector is pointing up out of the floor. And so we've got three vectors in three-dimensional space that don't all lie on the same plane, therefore they are independent. And so now you give me any B and there's one solution for it. Now obviously you give me a different B, there's one solution for that. It's going to be a different solution than for the first B you gave me. So it's not like there's just one solution for every B. I've said this before, but I want to make sure that's clear. Each B gives a different solution, but there's only, for a given single B, there's only one way to solve the problem. So, this row view has its advantages here and there, but the column view brings immense power. And that's what we're striving to harness, is that immense power of this column view. So let's revisit where we've been. We've got, on the left at the top, a set of linear equations, 3 equations and 3 unknowns. We can write them out here in this explicit matrix form, or better yet, just visualize it as, well, there's some matrix A times some vector X that gives us some vector B. I know A, I know B, I'm trying to find X. When does this work? And just reiterating what we had here before, it works when the columns of A are independent. It doesn't work when the columns of A are dependent. Now, if we didn't have this column view, you're going to be asking, when do I know that these 3 equations have planes that all intersect at one point? Looking at it from the plane point of view, that's a difficult problem or a difficult condition to encapsulate simply. But with the column view, simple. Just look at the columns of your matrix. Are they linearly independent? If they are, you're good to go. You're going to have a unique solution for each B. And that's the amazing thing. So this column viewpoint is the thing that lets us characterize the scenario extremely easily, at least in principle. It may take a little bit of work to numerically check it out, but we'll see some ways that we can easily check this out, and they're not that difficult. But the intellectual and insight power of this viewpoint is tremendous. Okay, so we're going to tuck in a couple ideas here at the end of this set of notes, just because they don't warrant an entire note set of their own, and we just needed to tuck them in here somewhere. So we've got this idea of the identity matrix, and we'll be coming up, we'll be using this coming up. So let's just take an aside here and introduce this. So let's introduce it through examples. Suppose we got a 3x3 matrix that looks like this. So it's got ones down the diagonal, and the off diagonals are all zeros. And suppose we put in some vector. That's 6, 4, 2. And so that vector is called the x, we'll name it x. Well, let's look at how, let's use our by hand view here to see how this works. Well, we're going to take the 6 and put it here. We'll take the 4 and put it along there. Take the 2 and put it along there. So the first element is going to be 1 times 6 plus 0 times the others. Just gives us 6. And so we can see that what's happening is the zeros are suppressing the other ones, and the 1 is just selecting out the one that we want. And so since we're selecting the first to go first, we're selecting the second to go second, and we're selecting the third to go third, this doesn't do anything. This matrix does nothing. What a slacker. You take I times x and you get back x. It hardly seems like it'd be something worth defining. But you know what? This is playing the role of the number 1. So when we have 1 times some scalar variable x, it just gives us the scalar variable x. So the number 1 plays an important role in the real numbers, as does 0. And now we're seeing that the identity matrix, this I matrix, we're using the symbol I because it helps us remember it's the identity matrix. It kind of plays the role of 1 in the AX plus B viewpoint. So the vector, any vector multiplied by A comes back out as the same vector. It doesn't change. So it's this special matrix. It's similar to 1 in the scalar world. And so here we showed a three-dimensional version of it in n dimensions. Everything off the diagonal is 0. Everything off the diagonal is 0. Down the diagonals, it's 1, 1, 1, 1, 1, 1, 1. And sometimes we'll use a subscript here, a single number, to show that it, what the dimension of it is. So, we might up here show I sub 3. Sometimes we'll say I sub 3 by 3, just as an alternate. And so in general, Ix equals x for all x. So this little symbol, this upside down A, means for all. So I don't know if you've seen that math symbol before. I suspect you saw it in your calc class, but just in case, I wanted to remind you of that. So that's the identity matrix, and then we'll finish off here reiterating our matrix notation. We mentioned this before, but we don't want to have to throw in a whole bunch of different letters. We'll just use subscripts to indicate the elements. So we've talked about this before, so I'm going to skip this. But this does show, how we read this. It's A sub ij, so sub just stands for subscript. And sometimes, getting subscripts, like if you're writing me an email or something, to write A sub ij is hard. And so instead you could say A parenthesis ij end parenthesis. So that means the same thing. So we can use either one of these forms. And to be honest, I prefer this, but sometimes this form just comes in handy. And so that's the end of this set of notes, and hopefully I've convinced you that the column view is the way to go. Much more powerful view. Occasionally we want to dip into the row view, but for the most part, we're thinking column view. All right, I'll see you in the next set of notes.